Hello everyone. So in the last lecture we already have seen the concept of density of states. We also have seen Fermi-level and the band model. So all three concepts that we discussed in the last lecture are very important. We need to know all these concepts in order to explain different phenomena that is happening or that usually happens inside a semiconductor device or in a semiconductor material. But today there are three other very important concepts that we need to learn. So the first concept is intrinsic temperature. So we will see what is intrinsic temperature, how intrinsic temperature is, or why this concept of intrinsic temperature comes into the picture as far as the semiconductor physics is concerned. We will see where Fermi level lies in an extrinsic semiconductor. For an intrinsic semiconductor, we know it's right in the middle of the band gap. But in case of extrinsic semiconductor, we need to understand where that Fermi level lies as far as the different types of dopings are concerned. And we will also very briefly in one slide will discuss what is compensated semiconductor, which is again a very interesting concept. We have to understand this particular concept in order to in order to have this in our mind, so that in future if we come across similar type of concept, we know how to deal with that. So with this we will start our lecture. Let's start the lecture.
So we already have covered the most of the topic related to the carrier concentration in equilibrium. So to start with in this lecture, I'll again discuss the carrier concentration in an n-type semiconductor with respect to temperatures. So in this case, the concentration of electrons are given by n0, that is concentration of electron in n-type semiconductor under equilibrium, and you have 1 by T in the x-axis. So it's like n0 versus 1 by T plot. Now as we already have seen that in this plot we have three different zones. One is intrinsic range, which is high temperature zone. Then you have extrinsic range, where your carrier concentration is constant. And then you have a low temperature zone, which is known as partial impurity ionization, right? And the equation associated with each zone is shown over here. So for intrinsic range, the carrier concentration can be expressed using this expression, that is root over NC/NV exponential minus Eg by 2 kT. In case of intrinsic range, it's constant. The concentration is constant, which is Nd. And then you have partial impurity ionization range, where the expression is root over Nc Nd exponential minus E ion by 2 kT. So we have expressed this formula by comparing the situation with the intrinsic range, right? In this case, as I already have mentioned, you have a band diagram wherein this is your Ed and this is your Ec. So this difference is known as E ion, and in this case all your carrier movement will be from Ed to Ec, right? So all the carrier movement will be from Ed to Ec, and that's why you can replace the Eg with E ion, and then your Nb will be replaced by Nd. This is what we have done in case of this expression, right? In case of this expression, this is exactly what we have done. Now let us look into the intrinsic temperature a bit more detailed way. Okay, so I already have said the temperature from where the intrinsic concentration starts dominating is the intrinsic temperature, right? So if you express this particular plot in this way, wherein you have impurity ionization with temperature and thermal generation with temperature, in this case we are plotting Nn0 with temperature, not with 1 by temperature. Okay, it's not the reciprocal in this case. We are plotting the this graph with respect to temperature. So for impurity ionization at low temperature, you will find that the concentration will increase. It will keep on increasing, and after certain value, it will saturate because all your donor atoms will be ionized. So after certain temperature, your concentration of carrier will be constant in case of impurity ionization. However, in case of thermal generation at low temperature, the electron hole pair will be less because less number of electrons and holes will be generated because temperature is low. After certain temperature, you will find that the thermal generation is kind of exponentially increasing. And this particular point where this impurity ionization and thermal generation, both the plots are meeting together, this particular point or the temperature corresponding to that particular point is known as intrinsic temperature. So if we define that, we can say that this particular point and the temperature corresponding to this particular point where impurity ionization and thermal generation plots are kind of intersecting each other is the intrinsic temperature. So after that, your thermal generation starts dominating. So if you look at this particular point, you can also say this is nothing but Nd, or this is nothing but the intrinsic concentration at Ti. Just look at the thermal generation plot. So it's nothing but the intrinsic concentration at temperature Ti, because thermal generation plot is drawn considering the intrinsic concentration only, right? So you can write Nd is equal to, at this Ti, at intrinsic temperature, your Nd, the concentration will be Ni at Ti. Okay, so now just put the value of Ni, that is root NCNV exponential minus Eg by 2k Ti, right? Instead of T, this will be Ti. Now from this equation, if you do a simple mathematics, then you'll find that Ti is equal to Eg divided by 2k ln root over NCNV by Nd. So this is your intrinsic temperature expression. Now it is very obvious, if your Eg is high, that is, if a material has a higher band gap, definitely your intrinsic temperature will be higher. Okay, and at the same time, if you increase Nd, the donor concentration, that also will increase the intrinsic temperature. So we have already shown a plot of Ti with the donor concentration Nd. Okay, so this is not in scale. You can look at different reference books that I have suggested. There probably you'll get this intrinsic temperature versus doping plot with scale, with numbers. But I have shown you the trend with doping, how the concentration is going to change. Say for silicon, it is increasing like this, and for gallium arsenide you'll find that at each and every point your intrinsic temperature is higher than that of silicon, because gallium arsenide has a band gap of 1.42 electron volt and for silicon it is 1.12 electron volt. So definitely the intrinsic temperature for gallium arsenide will be higher than that of silicon. In the expression itself, you'll find that it's a function of band gap energy. Higher the band gap energy, higher will be the intrinsic temperature, right? So this is how the plot looks like, or the trend looks like. Okay. Now let us see the Fermi level, where the Fermi level will be. Now if we consider the intrinsic semiconductor case, then you can write N0 is equal to Nc exponential minus Ec minus Ef by Kt, right? Now from here you will get the expression of Ef, which is equal to Ec minus Kt ln Nc divided by N0. This is what the expression of Fermi energy. Now in case of N-type semiconductor in extrinsic range, you can replace the N0 with Nd. We already have discussed. In extrinsic range, most of your donor atom will be ionized. So you can replace N0 with Nd. N0 will be approximately equal to Nd in extrinsic range. We already have explained in the previous lecture. Similarly, if you consider the hole, then your P0, the expression for P0 is equal to Nv exponential minus Ef minus Ev divided by Kt. So your expression will be Ef is equal to, that should be Ev. Okay, sorry for that. I beg your pardon. This should be Ev. Okay, please remember. So this is Ev plus Kt ln into, sorry, Ev plus Kt ln Nv by P0. So it's ln Nv by P0. So the P0 will again be equal to Na for a p-type semiconductor in the extrinsic range, right? So from these two expression, it is quite evident if you have an n-type semiconductor, your kind of Fermi level will be closer to Ec, because your N0, this value will be higher, right? Once this value is higher, the Fermi level will be closer to Ec. That is what we have seen. This, now the Fermi level goes close to Ec. Similarly, in case of p-type semiconductor also, you will find a similar effect. The Fermi level will be closer to Ev, isn't it? Now let us see the position of Fermi level with respect to intrinsic energy level, that is Ei. Okay, why we are doing this? Because we are also interested to see what is the deviation of Fermi level from intrinsic energy level. And that also will give us an idea that how far we are from intrinsic level. So for that purpose, we have considered Ei and just replace E with Ei in the expression. So you can write Ni is equal to Nc exponential Ec minus Ei divided by Kt. Now if you take a ratio of this expression and this expression, that is N0 by Ni, you will find Ef is equal to Ei plus Kt ln N0 by Ni. Now similarly, for n-type semiconductor, your N0 will be Nd in extrinsic range. And similarly, you will also find the expression of Ef. You will find the expression of Ef in terms of P0. In case of P0, it will be Ei minus Kt ln P0 by Pi. Similarly, you can do that. You can do this in your home as well. It's not very difficult. A simple mathematics or simple algebra, you can say. Okay. So similarly, P0 will be Na for p-type semiconductor. Now you can see that for n-type semiconductor, the Fermi level is above Ei because it's Ei plus certain energy, right? For holes, or for p-type semiconductors, your EI will be below, your EF will be below EI because it's EI minus ATLN. So again, if you dope your semiconductor with higher impurities, if it is an N-type impurity, the Fermi level will come closer to the EC, conduction level. And for p-type, if it is an p-type impurity, your Fermi level will go below the EI and come closer to NB. So here there is a pictorial representation. Okay. So you can see that for a certain concentration, the EF is somewhere for N-type. Okay. This is N-type. Okay, I have written here. So for N-type, you will find EF is closer to the EC and above your intrinsic energy level. Now from the expression itself, this particular gap is nothing but KTLN NC by N0. You can see here this value KTLN NC by N0. So it's like EC minus. So it's below EC. EC minus KTLN NC by N0. And for EI, it is EI plus. So this is KTLN N0 by Ni. That is what you'll find here. KTLN N0 by Ni. So it's like this gap between EI and EF. Okay. So more the doping, it will go even closer. Something like that. It will keep on going. Okay. This is how the Fermi level behaves in extrinsic semiconductor. Right. Now let us see that effect of temperature in Fermi level. So what we have done in this case is we have taken EF minus EI. Please note here, it's not EF, it's EF minus EI. Now EF minus EI is equal to 0 essentially means that your intrinsic energy is equal to your Fermi energy. That means your Fermi energy is at the middle of this band gap. That's why EF minus EI is equal to 0. Okay. Now, if you increase the temperature, you will find that your Fermi level is shifting for N-type from higher energy level to lower energy level. For N-type semiconductor, I repeat, for N-type semiconductor, your Fermi level will shift from higher energy level to lower energy level and will come close to the EI, that is intrinsic energy level, as we increase temperature. For p-type semiconductor, it will go up from lower energy level to higher energy level and will come closer to the intrinsic energy level, right? And higher the doping, this is the doping value, higher the doping, higher the temperature is required. Higher the doping, higher the temperature required to bring it back near intrinsic energy level, right? Which is understandable. If there are more doping, you need more temperature, right? So we also have seen at high temperature, the entire semiconductor starts behaving as intrinsic one. So the intrinsic or thermal generation starts dominating. Okay, that's why you'll find your Fermi level also is coming closer to the this intrinsic energy level. Okay, in this plot also it is quite evident. Okay. The next concept, which is also important, is known as compensated semiconductor. Now, in case of compensated semiconductor, you'll find that both kind of dopings are available. So you can write N0 plus Na minus is equal to P0 plus Nd plus. So it's kind of a charge balance equation. So you can write N0 is equal to P0 plus Nd plus minus Na minus. Now from here it is evident whichever doping is higher, the semiconductor will behave that way. If your N-type doping is higher, then the semiconductor will behave as N-type semiconductor, right? If your P-type doping is higher, then the semiconductor will behave as P-type semiconductor. Now in this case, there are a few compensation takes place. For example, if you have ED and EA both, For example, in this case, we have considered ND is higher than NA. That's why you'll find that there are more states in the energy level ED and you have very few states in the energy level EA. Now, the carrier will go from ED to EC in most of the cases here at a certain temperature. First, they will go from ED to EC. And for thermal generation, it's from EV to EC, right? And for ionization, it's from ED to EC. We already have seen this. Now, in certain cases, based on the kind of reverse doping that you have, which is Na in this case, carriers will come from ED to EA because electron will always occupy the lowest available energy state. So here the lowest available energy state is EA. So some of the carriers will move from ED to EA and rest will go from ED to EC. Now if your ND is higher than Na, definitely the semiconductor will behave like an N-type semiconductor. Okay, so this is what the concept of compensated semiconductor is. So one thing that you can note in this case is while we are discussing the intrinsic temperature Ti, we have seen it's proportional to Eg. Higher the Eg, higher will be intrinsic temperature. So one thing you can say that if you want to operate your device at a very high temperature, it's preferable that you take a high band gap material. I mean, based on this study, okay, there are other factors as well. There are other parameters as well. For example, mobility is again a very important parameter. But as far as this explanation is concerned, you can say that for high temperature operation, you will prefer a higher band gap material because your intrinsic temperature is high and your operation will be in the extrinsic range, right? This is how it looks, right? So it's T, it's like NN0 for N-type. So what will be your requirement? If you really want to operate your device at high temperature, you want this particular point, which is intrinsic temperature, to be in the right side, even at high temperature, so that your device remains in the extrinsic range, right? That's why I'm saying this is, from this explanation, one can say that for high temperature operation, a higher band gap material is desirable. But please remember, band gap is not the only parameter. There are other parameters also we should consider. For example, they already have said mobility, and there are some other parameters as well. We will see regarding this in the coming lectures.
So far we have seen what is intrinsic temperature, how intrinsic temperature is defined and why it is important. At the same time, we also have seen the Fermi level or the position of the Fermi level in the extrinsic semiconductor. Why this Fermi level is not placed right in the middle like an intrinsic semiconductor when it comes to extrinsic semiconductor. When you dope the semiconductor with certain material, how this shift of the Fermi level takes place. At the same time, at the end of this lecture, we have seen what is compensated semiconductor and why compensated semiconductor is important. So with this, I am concluding this particular lecture, but there are a lot more concepts that needs to be learned in order to understand various aspects of semiconductor devices and semiconductor devices based sensors. We will learn all these things in the coming lectures. Till then, thank you.